All right. Hi, welcome to the Collaboration and Communications session of VIS 2024. My name is Vidya Settler from Tableau Research. We have a really exciting lineup of 6 papers for this session. A reminder to all the attendees to please use Slido for posing questions and Discord for any continuing discussion you would like to have with the authors and the work. And also a special call out to the SVs who are helping with this session. A reminder that the total time for each presentation is 12 minutes, so please make sure you finish within that time so you have time to field questions. The first paper is StuGPTViz, a visual analytics approach to understand student-ChatGPT interactions. And the speaker will be Zixin Chen. He has noted that he's actively seeking potential internships or opportunities as a visiting PhD student, working on topics related to visual analytics and AI in education. So with that, Zixin, please take it away.
Okay, thank you. Can you hear me?
Yes.
Yeah, okay, great. Thanks for the introduction. So hi everyone, I'm Zixin and I'm the third year PhD student from Hong Kong UST. So today I'm honored to be here to present our latest works to you. It's on behalf of all my collaborators. So as you all have seen that large language models actually revolutionizing everything, like the tools we use, the workflow we apply, and also our mindset, everything has changed dramatically during the past years. And speaking of large language model in education, like our attitudes always change. Now, increasing number of studies start to emphasize the importance of embracing large language models like GPT into the education process. Like we should treat it as the tools, just like we first time have the calculators in the world. So after we have the calculators, our education focus can change more on the students like problem abstraction or problem solving skills. We do not mention too much about how fast or how accurate they can do some calculation online. I think that is the same for we should treat large language models just as a tools like this. So we already have plenty of works like use LLM for teaching and learning changes, but I feel like instructors still have concerns about student use of LLMs, just like our previous workshop has discussed. They are eager to figure out effective ways of harness the potential of LLMs appropriately. So we argue that it's the most important thing as the first step is to understand students' interaction with LLMs. Because based on this understanding, we can gain some pedagogical insight about student uses in their learning. With this insight, instructors can further provide some guidance on students. They can provide intervention if necessary. They can even redesign the learning materials to align better with the intended learning outcomes. So speaking of this pedagogical insight, we want to know first, what kind of insight instructors are interested at first. And we figure out that the first insight is the students' extent of their higher order thinking, like how much of independent thinking students have when using LLMs in learning. And also instructors want to know students' proficiency in use LLMs in their learning because they want to teach students who has the less ability to use these tools to better use this for their learning process. And we explored that for measuring of the higher order thinking, we can use the cognitive level from the revised Bloom taxonomy. Also for the proficiency of use the large language model, we can either like measure from the prompt direction, how much of the prompt engineer techniques they use. Also, we can from the output driven, like how much of the quality, how well is the quality of the large language model's response to the prompts. But still, we have challenge provide instructors with pedagogical insight because we are lack of the high quality data of student conversations. And also we don't know how exactly we can gain these insights from the analysis of the interactions. So to solve this challenge, we first integrate ChatGPT in our university's data visualization course. We designed multiple learning activities with our course advisor, and we classify these activities into each level of Bloom taxonomy to match and cover everything. We let students freely use this ChatGPT when doing these activities and collecting some high quality data. And to analyze this data, we design a coding scheme. First, to categorize students' cognitive level. So we code students' prompts into different level of revised Bloom taxonomy. For instance, if the prompt is like, what is data visualization? That will be the lowest level of cognitive process. Just some definition increase belongs to concept remember. And besides this kind of coding, we also provide codings from the prompt strategies, like some output restriction, like give me the response in 100 words, something like that. And we actually labeled every prompts we get from the students. And besides the prompts, we also evaluate ChatGPT response quality. So we design some metrics, like based on the information gain theory, try to quantify the amount of the accurate information provided by each response. So that's how we gain some numerical scores for each ChatGPT response. And together of this, we further mining all the potential code patterns to identify students' strategies when they interact with students. So we define two kinds of patterns or strategies, like either is ordered or is unordered, all based on the code we generate previously. So for instance, if I ask GPT first, what is visualization and what is human-computer interaction, and that will be definition inquiry. And after that, if I ask a follow-up question like, so what is the relationship between these two concepts? That will be a follow-up questions like with the order after the definition inquiry. So in this way, we actually label everything we have and mining every pattern we can gain from the conversation data. So based on all of them, we design a system, Student-ChatGPTViz, try to let instructors do the exploration for the insight themselves. And the first filter view will offer an overview and enable some filtering of tasks and students based on the background information. For the pattern view, we not only provide the macro level conversation summary, but we also provide micro level interaction patterns. So specifically, like we use the sequential color scheme, like same with previous coding, from light yellow to dark brown to denote the increasing cognitive levels. And we have the distinct color for the prompt strategies. Thus, we can easily summarize and compare the interaction patterns between groups and within each group. We also have like summary for ChatGPT response quality and student learning outcome for reference. And actual functionalities and for grouping and background information is also provided. So like speaking of previous patterns we mined, like we summarize everything in the pattern mining table provided for instructors to do exploration. And together with this table, we can also let instructors to trace the detailed evolution of each student's interactions, as well as ChatGPT response quality for a specific task. So here, each pass in the tree represents one conversation for one task, and one node here in the task pass represents one student prompt, and the length of this edge, the horizontal projection of length, represents the information gain from this prompt. At the end, we also provide background information tag for instructors. So besides this previous understanding and analysis, we also provide background and detailed descriptions of the original task and conversation data for instructors to check manually. To evaluate, we provide several case studies to show that the system can not only provide personalized feedback to students. So for instance, instructors may figure out this student CX like has plenty of interaction with GPT, but has a very low score. So through the pattern mining table, he can identify the students have plenty of the basic question inquiry, just copy and paste the question to the GPT. And together with the interaction tree and also the original context, instructors figure out that these students tend to like use some very basic interaction for the multiple choice question. But on the other hand, for the visualization analysis question, even with a low score at the end, he showed more in-depth thinking. So we can like have more this kind of question for the students to improve his learning process. We also have case for course material redesign or identify some effective interaction strategies to have the feedback for the students. That will be some case. Also, we evaluate students' experience of use GPT to learn, our metrics quality study, and also the system's usability. Some other insights we gain is that we think we should redefine the ChatGPT in education from a universal solver to a pedagogical partner, emphasize the critical thinking of students. Like we encourage students to use GPT for alternative design generation with rationales and enable them to choose from these options to generate their final designs. And as a takeaway message, so we use GPT into the course to collect the high quality data set, and we design the coding scheme and metrics for analyze these GPT student interactions. Finally, we provide a VIS system like instructors to have like insight exploration by themselves. And please check the details about the papers like from the QR code. And thank you very much for your listening. I'm open to any questions.
Thank you so much, Zixin. While we get maybe a question from Slido, I'll ask a quick question here because we're almost out of time. So given kind of your insights in your work in how, students' cognitive levels and interaction patterns affect how they, interact with your system, how do you think that this tool could be adapted in the future to help instructors proactively identify and address, potential biases and responses that could affect student learning, just given this uneven skill level that you've seen?
Yes, thanks for the question. So like one of the exploration we find like is previously for the visualization evaluation type of question, this kind of question we need to have some redesign. Like for instance, previously we might ask students to evaluate a visualization based on like blah 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 methodology or rationales. But for later use, we do not really need to provide them the detailed rationales to them. Otherwise, they can just copy and paste everything to the GPT. But we could provide more vague instructions on the questions. So this kind of the redesign and the testing of previously learning paths for students, I think is what we can do with the system. We can use the system to check whether the previous learning activities, learning material design is still aligned with the learning goals after we let students to use GPT, because anyway, we cannot avoid it. So we should find better ways to align the design of the goals, design of the task to better reach our goal of education. I think that is the most like significant part we can use with this tool. Thanks.
All right. Thank you so much, Zixin. So we are out of time, unfortunately, but please use Discord to continue engaging with the authors. But let's give Zixin a round of applause, and let's move on to the second talk here. So the second talk is SLInterpreter, an exploratory and interactive human AI collaborative system for GNN-based synthetic lethal prediction. And Haoran Jiang will be presenting this work. Thank you.
Okay, thank you very much. And I'm not sure if my slides print well.
Yeah, we can see your slides. Yeah.
Okay, thank you. Hello, everyone. Greetings from Tampa. And my name is Haoran Jiang from Shanghai Tech University. I will introduce SLInterpreter, an explorative and interactive human collaborative system for GNN-based synthetic lethal prediction. And the synthetic lethality refers to a situation where mutations in either two non-lethal genes do not affect survival, but when both genes are mutated at the same time, it leads to cell death. Malignant tumors accumulate a large number of gene mutations due to errors in DNA replication and repair. So inhibiting another gene that has a synthetic lethal relationship with these mutated genes can selectively kill tumor cells without affecting normal ones. In recent years, the principle has been applied in targeted cancer therapy and holds great potential. Currently, common methods for validating SL relationships include wet lab techniques, such as RNA reference and gene editing like CRISPR-Cas9. However, wet lab experiments are resource-intensive, time-consuming, and carry the risk of off-target effects. Additionally, with over 20,000 genes in humans, it is nearly impossible to screen all possible pairs. As a result, many efforts have begun to use machine learning methods to predict potential SL pairs. Although these methods have been improving in accuracy, they still lack the interoperability to convince domain experts. Furthermore, it is difficult for experts to effectively correct model errors or explore potential mechanisms using these methods. Most computational methods for predicting SL pairs overly rely on certain manually set rules or assumptions, leading to issues like poor prediction accuracy and difficulty in discovering new mechanisms. Therefore, we opt for a weak assumption GNN model for prediction. Additionally, most work focuses on helping AI experts modify and fine-tune GNN models, as seen with tools like Corgi and GNN-lens. We focus more on enabling domain experts to explore the mechanisms behind predictions and enhance interoperability based on domain knowledge. And to handle these challenges and gaps, we come up with this research. We track the daily workflows of domain experts and conduct interviews to understand their design needs and expectations. Then we developed an iterative human-AI collaboration framework to meet their design needs, empowering domain experts to explore new SL pairs and underlying mechanisms. This framework also assists in the iterative optimization of knowledge graphs, enhancing experts' trust. Finally, we evaluate the effectiveness and usability through a comprehensive case study and several interviews. So we began with an observation study, interviewing a team of 4 SL researchers and 2 clinics. From these interviews, we distilled 6 key design requirements, including providing clear present and summaries of explanation paths for prediction results, detecting relevant training data corresponding to wrong or noisy paths, and offering insights for mechanism exploration. And our pipeline consists of a data processing module for processing knowledge graphs and extracting gene features, such as sequence and descriptions. The backend trains the GNN model and return prediction results along with the corresponding explanation paths. Lastly, the front end provides interactive granularity SL analysis through several interconnected views. And the dataset includes 42,547 entities like genes or biological processes, and 33 types of gene relationships. Additionally, there are 396,619 triplets used to connect these entities and construct the whole KG. All the data comes from public datasets, including NCBI, SLInterpreter, and Pretain KG25. Our backend system is based on KR for SL, a sort of model for SL prediction. This model combines the structural semantics with the textual semantics. The final decoder ranks candidate genes based on the confidence of forming SL relationships, selecting the top 50 as prediction results. The model outputs 3 whole paths as explanation paths for interoperability. And the front is composed of the 4 parts. And the top are 3 search boxes. User can first select a specific disease to narrow down the range of gene selection. After choosing the primary gene, the table below will display all potential partner genes ranked by confidence. Below the search box is the operation list, which records all path deletion actions. At the bottom is a model log, which displays performance for each iteration of the model and provides options for selecting different models. In the upper middle section is a gene embedding view, which displays the clustering of gene after dimension reduction. Hovering over a gene, the radar chart is arranged to display the distribution of its potential partner genes, allowing users to quickly identify the clustering patterns of the candidate genes. Each gene is also represented with a clock hand sign to indicate the ranks of different genes. To ensure usability, we incorporated semantic zooming and lasso selection. allowing for more flexible interaction and exploration. On the far right is an interpretation view, which is designed to display the explanation paths of different predictions as well as the flow distribution among various entities. This allows users to observe potential common patterns in the explanation paths. On the bottom left is the KG view, which displays the two hope entity connections starting from the selected gene. On the bottom right, the modifier view displays the selected path, and two bars on the far right show the proportion of different granularity strategies selected. These bars assist user to choosing the appropriate granularity strategy to delete wrong or biased data. And about the data modifier design to help users select appropriate granularity strategy for path deletion. We define the granularity levels flow. In this diagram, H represents high granularity, which includes broader entities such as gene, biological process, and the preterm functions like that encompass numerous lower granularity entities. And L represents low granularity entities such as specific genes like BRIC1 or specific preterm functions like DNA repair. As users progressively select more edge from moving from right to left, the overall granularity increase and the number of paths represented decrease until they find it appropriate, which will ensure a smooth transition in granularity, avoid sudden jumps, and allow users to refine the granularity strategy incrementally to the level that user expects. Based on this rule, we design the corresponding interaction view, and the user can choose between high granularity and low representations. For example, in this case, the blue box labeled A1BG represents a low granularity entity, while the red box labeled gene represents a high. By selecting different granularity levels, the two bars in the path level summary on the right will update to display the corresponding data. The primary bar on the left displays the proportion of paths that include at least one low granularity entity compared to paths that contain no low granularity entities. The secondary bar on the right displays the proportion of paths that contain two low granularity entities compared to those that contain only one. The currently selected representations are connected by lines which differ in terms of being solid or dashed based on the granularity level. Let's take a simple example. The current granularity selection is HHL, which means it includes all paths while any gene is connected to the biological pathway IL-6 through any relationship. We can observe that the HHL paths account for a relatively small proportion within the highest granularity level, around 30%. At the same time, HLL accounts for a high proportion within HHL. This indicates that most of the paths from genes to IL-6 node are connected through the participant GPPW biological relationship. If the user determines that genes should not be connected to IL-6 via participant GPPW, they can choose the HLL path strategy instead of HHL, ensuring that no unnecessary paths are included during the deletion process. Next, I will introduce our evaluation to the system. In the first exploration circle of the case study, the domain expert conducted a simple exploration of the prediction results for CDK1 to MYC. By examining the radar chart in the embedding view, they identify a cluster composed of correctly predicted genes and also noticed data associated with some clearly incorrect predictions. He used the data modifier to delete the paths that he considered incorrect. In the second exploration circle, he noticed a slight improvement in model performance, and the prediction results aligned more closely with his expectations. By observing the proportion of explanation paths for clustered genes, he concluded that EGFR likely shares a similar underlying mechanism with the other two correctly predicted genes, making it worth further validation through wet experiments. The participants saw the system design aligns well with their usage habits and helps them quickly check prediction results and explore underlying mechanisms. Using the system allows them to more efficiently filter prediction results. However, they mentioned that certain fields in the system have a learning curve requiring at least 20 minutes to fully understand and master. The current prediction model only consists SL pairs involving a pair of genes. In the future, we aim to extend the system to support more complex network analysis involving multiple genes. Also, we plan to integrate more biological data into the system, and then we hope to extend the system to cover a broader range of GNN prediction tasks. And the above outlines the key contributions of our work. And that concludes my presentation. Thank you very much for your time and attention.
Thank you, Haoran. I don't see any questions on Slido just yet, but I'll ask you one quick question. Um, so I'm curious, in terms of scaling your SLInterpreter framework, what challenges do you anticipate that could add complexity to both the data processing side and the model interpretability? I mean, for example, extending the analysis to more complicated networks involving multiple genes. So just if you could speak for that scalability, that would be great.
Oh yeah, I think it's a very good question, and some recent research has shown that maybe three or more genes can have the SL relationships as well, and that kind of interaction between three or more genes are very complex since they don't just not often appear often in the so we don't have too much data about these situations. So it's hard for the GNN model to learn that kind of situations. But maybe we can see some if we can have more data about these situations, and we can make more clear presentation of present of this complex network of these interactions. I think we can make much more um, progress in that kind of situation. Yes.
Okay. Well, thank you so much. Please, I didn't see any questions on Slido, but please continue that conversation, in Discord. So let's move on to the next speaker. Thank you very much, Haran.
Okay,
So
thank you very much.
yeah. So the next paper is VMail, 3D enabled correspondence about spatial data on almost all your devices. And the speaker is Jiang Hu Nam. Yep, we can see your slide, Jiang. So please go ahead. Thank you.
Yeah, thank you. Thanks for the instruction. And I'm honored to present our work that did with Tobias Isenberg and Daniel Keefe. So researchers in the field looked at different ways of telling data stories, and one could present data through familiar storytelling mediums or add interactions to storytelling or invite others when creating data stories. And to better communicate insights, people have used animations and annotations and lightweight sharing mechanisms. And we built upon this prior research on storytelling and communications to introduce a framework for collaborative data visualization. So we call this a framework VMail, short for visualization mail. The key idea is to correspond easily via whatever devices happens to be handy between team members. The approach is flexible exports of visualization results that could be viewed at different fidelities and be extended using our clients to ask further questions and provide feedback. So let me show you some example scenarios. So there are three users collaborating around visualization application. So a typical session starts with the receiving a message with an URL. So the student receives a message from a developer, and you can see this in just like a normal message in Slack or whatever tool the team uses for the communication. And it includes a URL, which brings us to the message in a video form. Play the video. So Because the student is on their laptop where they have 3D visualization software with their female plugin installed, they can also open the message in the software, and the message transforms from a video file to a live interactive 3D visualization. Do you hear the audio from the video? Sorry.
Yeah, we're not hearing any audio. I was going to ask.
Okay. Okay.
Yeah. Is it possible to talk over it?
Yeah. Okay. Sorry about that. So yeah, here it's interactively creating the data stories. So here I'm a student done creating the animated data stories. So I'm going to create a message and upload to the server and copy the URL and send that to email to my advisor. So sorry about the problem here. So inspired by our daily use of traditional emails to correspond easily via whatever devices happens to be handy, Vmail also provides accessible options for users to look at visualization results in detail and provide feedback. So here's the professor at a coffee shop waiting for someone to join. While waiting, he takes a quick peek at the email from his student. So I'll be pretending I'm a professor here. No, not this one. Oh, yes, this Eddie. Let's open it up on the mobile phone to see in more details. Yeah, not this one. Yes, this one. Let me double check to make sure. All right, I'm gonna tell him why this is the case. Okay, I'm done. So I'm gonna hit upload and share that to my student. So we address these sub-challenges for collaborative scientific data visualization. Due to time, I will focus on the first and the last points. First, we provide means for conveying spatial information. So we represent data views as 3D frames to show locations told in the story. Also, having the 3D frames, we can visually reference these 3D locations in annotations. And finally, to convey how these spatial data views are related to one another, we break the animation into steps. So we first move the camera to the next location and change values of visualization states. So in this example, animation shows changes in the color map. And different data glyphs applied to the water masses. To address the last challenge, we support lightweight clients for collaboration. So when the user creates a story, our framework generates several files, and one is a video file showing the final animation, and our web client simply plays the video file. So comments are shown as subtitles, and drawings are overlaid onto the video. Keyframes are shown as chapters if the video player supports that feature. And our mobile client is like a special video player with additional features for interactive storytelling and making annotations. So users can use the mobile client to look at the animation in more details and leave feedback without opening the data in often complex 3D visualization applications. So let's look at some additional features of our mobile client. So the client shows which portion of the video are important and provide a feature to play the video in the reverse direction. And a feature to look around. It uses 360 view images saved when creating a story file. To see how our tool applies to data collaboration, we asked a research team composed of experts from different fields. The team decided to use our tools to create data videos showing findings from their data. On ours, and the writer created an initial video and showed it to scientists for confirmation and possible feedback at the end. The final video shows a fly-through animations of 3 important regions in the data. Each region is told with 3 data views, and the last data view in the animation shows a closing remark. So participants indicated the comments, helped them clarify tasks and provide immediate help. And it was interesting to see the comments had these imperfections like typos and cap lock errors, giving us this casual chat-like communication feel. And we think this is interesting to see this casual informal style of communication in high-end scientific communication. And we believe this encourages more free, open discussions among participants from different backgrounds. And in the future, we like to look at other devices. For instance, what would it mean to see 3D drawings made in VR on mobile phone? Would it make sense to see these data stories on a smartwatch or even on a postcard like the ones from Dear Data? So when we think about device ecology, we often think about remote rendering. Even though this technology is really useful, instead of trying to port high-end visualizations across all the devices, it might also make sense to incorporate visualization and storytelling techniques unique to each display device into one collaborative framework. And we hope VML provides the initial steps towards that goal and provide the evidence that stories are good base construct and the motivations to bring these devices into one framework. Thank you.
Thank you so much, Jiang. That was a really cool piece of work. Sorry that you had some audio trouble, but I felt like you did the impersonation quite skillfully.
Yeah, it was scary too.
Yeah.
Thank you.
Yep. We have one question on Slido that I'll read out to you. Interesting work. How do you define camera move between different keyframes?
Camera move defined. So when the the voiceover of the video should have told, but there's like a plus sign that when you click on it, it kind of captures the current camera view. So when there are multiple, it just like interpolates between the camera's views in the keyframes. But as I showed in the videos, if there are values of visualization states, like data changes, it kind of do the blending, like move the camera first and then do the blending if there's no interpolation between.
All right. Thank you, Jiang. That's all the time we have, but thanks again for your cool work.
Thanks much.
We will move on to the next paper. The next paper is a Deixis-Centered approach for documenting remote synchronous communication around data visualizations. Shaohan will be presenting this work.
Hi, thanks for the introduction. Hi, everyone. I'm Shaohan, a PhD student at the University of Utah. Today, I will talk about a Deixis-Centered approach for documenting remote synchronous communication around data visualizations. In linguistics, deixis refers to the phenomena that the meanings of certain words depend on the context. These words fall into three categories: personal, temporal, and spatial. This work is about deictic gestures in visualizations, so it will focus on spatial deixis. The following sentence contains all three types of deictic words. In the spatial deixis, right here refers to the location the speaker is pointing at, and the pointing gesture here is apparently essential to convey the meaning, which is an example of how people use a combination of verbal and nonverbal expressions to communicate meanings. While verbal communication is typically the primary mode, nonverbal cues are also critical. In this work, we choose online discussion session as a scenario to explore nonverbal cues in communication. In this case, the nonverbal cues could include drawings that people made to direct attention, indicate clusters, or outline boundaries, and so on. And we can imagine that these nonverbal cues are especially important in less rehearsed, small collaborative meetings where the visuals are raw and under-annotated. In a real-time meeting, the speaker encodes meanings through both cues for the receiver to decode. Documentation complicates this process by re-encoding the meaning into documents for later interpretation, and thus the quality of the documentation is crucial to the information received. Currently, there are three mainstream ways for automatically documenting remote meetings, but they each have flaws in capturing deixis. Transcripts with or without accompanied screenshots will miss deictic gestures. Video recordings, on the other hand, can be hard to navigate and can sometimes also fail to capture the cursor movement. We present a framework to automatically document remote meetings. It works by pairing deictic gestures with words and use the extracted pairings to generate interactive documents. Now, to begin with, we need to understand the possible ways to perform deictic gesture and how they differ in execution. From existing collaborative meeting tools, we identified three common methods of expressing deictic gestures: laser pointer, who leaves trails that disappear after a short period; durable pencil; and various interactions that can serve deictic purposes. Then we conducted a formative study to analyze the use of these tools. Due to the complexity and diversity of interactions, we excluded them from the study and only implemented a proof of concept example in our application. We found that the laser pointer has a higher use frequency, but often lack precision, while the pencil tool has a lower usage rate, but are generally more accurate. In the great talks by the late Hans Rosling, he would frequently use hand gestures to direct attention and express emotions. We found that in remote settings, the laser pointer is used similarly to direct people's attention to a specific visual object and can sometimes express emotional intensity as well. The use of pencil, on the other hand, is much like hand-drawn annotations in asynchronous collaborative platforms, typically more complex and lasting for at least a portion of the discussion. Our pipeline starts with an interface that enables all these deictic gestures we have discussed. It also collects audio recordings, pen trails, and interaction states, all synchronized with timestamps. We then pair utterances with gestures based on the timestamps we previously collected. And then we extract word-level references using the in-context learning capability of large language model. And following previous works on meeting transcription, we also tried to produce meeting minutes to provide more readable contents. With respect to the deictic words, Some are successfully merged or preserved in the meeting minutes, but some are lost during the transition. Even the model is prompted to preserve it. The generated interactive document looks like this. With the mouse hover over the blue text links, the canvas switches to the corresponding chart and plays the annotation. While the timestamp links are used to trigger durable annotations and interaction states. We conducted a user study to evaluate this tool. We recruited 9 pairs of participants to discuss given visualization remotely using our customized interface, and then let them review and rate the generated interactive document. User evaluation shows that people in general prefer this tool, saying that it makes it easier to get the context and reduces cognitive load for taking notes. We found more patterns of using didactic gestures during the user experiments. First is that the same intention can be served by multiple distinct gestures. For example, this circle refers to a time interval. A line or 2 smaller circles can express the same intention. Second, the meaning of didactic gestures relies on the accompanied verbal expression. For example, this image with the accompanied words refers to the nodes within this circle. But with different verbal expression, it can mean the opposite thing, nodes beyond this circle. Also, gestures with similar shapes can have various meanings with different accompanied verbal expression. For example, a circle can mean position of a missing element, connections between nodes, and time interval. Third, gestures often convey dual meanings. For example, this gesture conveys 2 meanings. First, it directs attention to the line chart, and then it indicates the reading direction with its motion. We present the first preliminary taxonomy for didactic gestures on visualization contexts in remote settings. We got 9 types of intentions, each with various expressions. More details can be found in the paper. To get a little bit further, didactic gestures we have discussed serves as a bridge between language and visualizations. And the bridge do not only exist in verbal communication, similar concepts apply to written communication as well. For example, people use colors, lines, or both to connect visual elements with text. Viewing these visual cues as didactic gestures may offer a new perspective for understanding existing challenges such as captions, annotations, and text augmentations. Thanks for listening. And I'm not sure if that counts for job market, but I'm looking for a research internship next summer.
Thank you so much, Chang. Let me just see if there's anything. There's not a question yet on Slido, but I have a question I wanted to ask you. I really like this taxonomy of didactic gestures. I think that could be really interesting in kind of furthering this space of interactive viz and just multimodal interaction in general. But could you comment upon how your system differentiates between these more meaningful referential gestures and some non-essential ones like doodling, during a boring meeting, for instance, and how that impacts the accuracy of, identifying these meaningful gestures?
Yeah, that's a very good question. I did not talk about it, but we encountered that problem during our implementation. So because as we have discussed, the gestures all have different shapes, so it's hard to tell just by the gesture whether it's meaningful or not. But we did we did screen out some gestures based on the accompanied context, the accompanied verbal expressions. For example, if someone is not saying anything or is just saying that, then it's very possible that this gesture is just a doodle and it's not meaningful, and we filter that out. So it's all about verbal expressions, I guess.
Yep, that makes sense. Well, thank you so much, Chang. Nice work. Let's give another round of applause, and let's move on to the next paper in the session. The next paper is eliciting multimodal and collaborative interactions for data exploration on large vertical displays, and Gabriela Molina-Leon will be presenting this work.
Hi, everyone. I hope you can hear me.
Yes.
Yes, thank you. I will first present to you this paper titled Eliciting Multimodal and Collaborative Interactions for Data Exploration on Large Vertical Displays. This is research I conducted together with my co-authors, Petra Isenberg from INRIA in France and Andreas Breiter from the University of Bremen during my PhD research. So yes, first of all, I would like you to shortly reflect on the scenario I show in this picture. Imagine you are working on a large vertical display, you are working with a colleague and want to interact with some data visualizations. How do you do it? Probably you do it, for example, with a mouse from a desk, or as in the case of the picture, if you notice the display has touch capabilities, you could use your fingers to tap on the visualizations. However, in this study, we were interested on how would you like to interact with data visualizations on large displays. For this reason, we conducted an elicitation study. So for those of you who are maybe not familiar with this type of methodology, an elicitation study is a study where you recruit people to ask them for creative ways of performing a task. In this particular case, we were interested in finding out what input modalities people prefer for exploring data visually on such a display. We gave them 4 different modalities that they could use. One was touch gestures, another a pen, speech commands, and finally meter gestures. We recruited for this study 20 participants organized in 10 pairs, and we were interested in recruiting people that in their everyday life, they work with data visualizations. So the idea of the study is to ask people to come up with different ways of interacting with the data visualization, regardless of the technical limitations. So for this study, we defined 15 tasks that we took, for example, from different task typologies as the one of Andrinko and Andrinko. We were interested in exploration of spatiotemporal data, so we focus on the exploratory task. And we also collected tasks that are particularly suitable for large vertical displays. So for example, you here see on the right a diagram of a task. So this task was about multiple coordinated views. In large vertical displays, of course, you have a lot of surface to cover, so you can use multiple views. And in this situation, we ask people to change the layout of these 4 views. So you have a grid of 2 by 2, right? And we ask the person to simply change the layout to change to a grid of 1 by 4 without changing anything of the visualizations. So every person in this study had to propose an interaction. The way we supported this was through the Wizard of Oz techniques. So there was no real system implemented behind. People came up with their ideas, and we used the Wizard of Oz technique to somehow imitate how the interaction would have an effect on the system. As I mentioned before, we recruited 20 people that were organized in pairs because we're also interested in taking into account the collaborative aspect of this situation. And each person had to make at least 3 proposals on how to interact for each task. At least one of these proposals had to be multimodal, so it had to combine at least 2 of the 4 modalities that were offered, and at least one of them had to be collaborative, which meant that the 2 people had to work together in the interaction. So here I show you an example on how this worked. So people, in this case, the person on the right she makes a speech command, the other person taps on the screen. So this would be a collaborative interaction where it's also multimodal because touch and speech are combined. So the paper, of course, has all the details, but here in this presentation, I want to give you an overview of what we found. We collected 1,015 proposals, so for all these 15 tasks. And if you group them together, depending on how, let's say, how they overlap with each other, we got 360 distinct interactions. On average, for each of the 15 tasks, people proposed 27 different ways of performing the interaction. On the opposite plot that you see on the right, you can see, for example, that 1/4 of all the proposals were speech commands. So given the opportunity of using these 4 modalities, alone or in combination by one person or multiple ones, 1/4 of all the interactions were speech commands, which we found certainly a very interesting result. If you have a look at the second group, another 1/4 of the proposals were multimodal, and they combined touch and speech. This was regardless of the order, though, so it could be that touch is first and speech later, or the other way around. As I mentioned earlier, for each of the at least 3 proposals per person, one of them had to be multimodal, right? So that means 1/3 roughly of the proposals that people made should be multimodal. And actually, we found that in total, 42% of the proposals were combining 2 or more modalities, which suggests that people were interested beyond, let's say, fulfilling the requirement of our study on combining the 2 or more modalities. In particular, the most common sequence that we had in the study was a touch gesture followed by a speech command. Here, for example, I show a case of filtering when one person tapped on the elements in the visualization and then used a speech command to remove other elements. In particular, in an elicitation study, one of the main outcomes is what we call a consensus set. So this is a set of the most common preferred interactions for each of the 15 tasks. So, right, if we have 15 tasks, then we have 15 interactions that compose the consensus set. So of the 4 modalities, the meter gestures did not make it to this group. And actually, we had touch, pen, and speech commands. So for example, for touch was the most preferred modality for showing tooltips, moving and resizing views. So here you see, for example, 2 people using their fingers to resize a view. The pen was the preferred modality for 2 tasks, which were selection and adding annotations. And for everything else, speech commands were preferred. So for example, we had deselecting, we had filtering, we had sorting. All of this were speech commands alone. We also calculated other metrics. You can have a look on the paper, such as highest max consensus, which denotes, for example, how much consensus was in the proposals. So in the case, we had one task of adding a regression line, and in that task, 95% of the people suggested that one way to do it was with a speech command just saying add regression line. And regarding the multimodal interactions, we identified different groups. So for example, following the work of Morris in 2012, we identified what she called multimodal synonyms, which is, for example, when you conduct one same action, you can do it with one of 2 modalities. So for example, if you have drag and drop, sometimes people would do it with touch, so they would go and approach the screen and touch it, but sometimes they would use the same action just without touching the screen, which then would be a meter gesture. We identified what we called collaborative synonyms, so it's an equivalent concept that is shown on the pictures on the right. So you have here, for example, the same action happening in both pictures, but in the top one person is conducting the action, and in the bottom, 2 persons are doing it. So it's collaborative synonyms because the only thing that changes is the amount of people involved. And we also noticed that when people use multiple modalities was because they divided a specific task in 2 or more steps. So for example, for adding an annotation, people said, okay, step 1 is tapping the place where I want to put the annotation. For this, they would use touch. And then for adding the annotation itself, the text, they would use a speech command. In general, we noticed that when people interacted together, they either used 2 modalities in a sequence. So as you see in the photo on the top right, or they interacted simultaneously, as you see in the bottom, where let's say two people are acting at the same time with touch. So in conclusion, what we found in this study is that given a set of different modalities and different ways of collaborating, people overall prefer unimodal interactions. However, if we would like to support all the tasks that we investigated in the study, we would need to build a system that supports speech, touch, and pen interaction. This overlaps with previous work that, for example, indicates that although multimodality may be suitable and beneficial in different situations, sometimes people may not use it even if they can. And what we found very interesting of our results was that speech interaction was so dominant in the preferences. Furthermore, we had asked people about their previous experience with speech, and 65% of them had said that they had never interacted with speech, even though they really preferred it in the study. So of course, this leads us to other questions, like for example, would speech be as preferred if we would actually build a system where this is where all these interactions are supported? And in the context of collaboration, which we were of course also considering, how would these different modalities affect the way people collaborate? In this study, our results were in the end personal, but we were also interested in the collaboration. So if you want to know more about these topics, please stick to with me for the next talk, because it's also a paper following up. Thank you.
Thank you, Gabriela. Really nice work. I don't see anything on Slido just yet, but I was going to follow up on what you just posed as the takeaway. So you mentioned, that participants seem to prefer these unimodal interactions, right? And specifically speech, despite this availability of multimodal options. But I'm curious, we've seen this increasing prevalence of multimodal systems in any case. And, people always say it's best practice to have, multimodal availability. So I'm curious, what are the potential implications for designing collaborative data exploration tools? Is it that we might want to explore other types of tasks that would encourage multimodal interaction, or, simply one modality tends to be dominant over the other? So what is your take on kind of straddling that dichotomy here?
Yes, on the one hand, we focus on low-level tasks. So I think if we, for example, consider, let's say, higher-level tasks that we can then decompose on smaller bits, chances are this would lead to a multimodal interaction, right? So we try to focus, let's say, on the smallest elements that would anyways be present in any task. So I think from that perspective, let's say it's not fully discouraging that multimodality would not be supported. And I think on the other hand, it also, something that often came up in the study is that people really appreciated having different ways of doing the same thing for accessibility reasons. And I think that's, for example, an important topic that we are increasingly discussing in the community. And then having multimodal interaction support that, of course, could help different people interact different ways, which then certainly would suggest that we should bring multimodality forward.
Okay, well, thank you so much. Let's give a round of applause to Gabriela for that paper, but she is not going anywhere. So she has another paper, and that's nice transition there, just to the next slide. So her next paper is Talk to the Wall, the Role of Speech Interaction in Collaborative Visual Analytics. So go ahead, Gabriela.
Yes, thank you so much. And I hope I can keep you here up until the break. So as I mentioned earlier, we in the first study, we investigated how people prefer to interact. But of course, it brings up the questions, what would they do if they would have the chance to execute these interactions in a real world system? So for this reason, we conducted this follow-up study inspired by the elicitation study, where we actually implemented a real-world system that would support, in this case, collaborative sense-making on a large display. In particular, as you see in the picture, it was a wall-sized display. So what we did in this study is that we gave people, in this case, also a pair, a task. And so we were inspired by the 2006 VIS challenge, that is a dataset that has been often used in previous work to investigate collaboration. And in this task, people are required to solve a fictitious mystery. So it's a bit like escape room, a group game-like activity, where these two people need to, in this case, explore a set of documents. And while they're interacting, they have different possibilities on how to collaborate, and then we investigate how they do this. So in this particular case, we built a system, a web-based system in the wall display that supported 20 tasks. Many of them were inspired by the tasks of the previous study, but also some were suitable to this particular data set. And here people had the opportunity to interact either with touch or speech commands. So here you can see the system in action. The idea was that we would provide 20 different tasks or actions that people could perform. They could do it either with touch gestures or speech commands. It was totally up to them. We implemented this system so that they could choose not only how to interact with the system, but also how they would collaborate with each other. And then we were interested in finding out how the modalities may affect, let's say, how the interaction choices may affect the way they collaborate. This was then a technology probe that we used, and we also provided the source code as part of our paper. So yeah, similarly, I give you here only an overview of what we found out in this study, but so we were interested in seeing whether speech would be as dominant as in the previous study. And as you can see from the graph on the right, that was actually not the case. So touch, let's say not fully unexpectedly, was the most common modality used for the different tasks. However, we noticed following up also on the specific tasks that were highlighted in the previous study, that speech interactions seem particularly suitable for a specific task. For example, for sorting the documents of the dataset that the people were working with, for text selecting all, for clear highlighted documents. So global operations, this means that operations that once they would take place, they would affect the whole dataset, and of course what both people were doing. There were also interesting cases. For example, we did not only log, let's say, what people did, but also we asked them later, how would they prefer to interact? And here you can see for the task of searching, so searching a keyword in the documents or clearing that search, although in the study, people certainly use touch most, when we asked them how would they prefer to interact, the majority were either preferring either speech or touch or also speech. So we could see also that there was some differences between what people actually did and how would they have preferred to interact. Furthermore, we also looked into personality traits in this study, and this was an interesting aspect that came up in a pilot study. So when we first tested the system, one of our participants mentioned that they were a shy person, that they would, let's say, in the real world would not be so eager to talk to people a lot. And so why would they do this with the system? And we found this a very interesting comment, because it suggested that maybe the personality traits of a person may influence their interaction choices. So this is why we looked at 3 personality traits, which were agreeableness. This means how likely a person it is to cooperate, so how likely they are to work together with someone. Extroversion, which means, of course, how extroverted a person is, and how open they are to new experiences. And we thought, for example, if people were agreeable, they would use speech less. If they were extroverted, they would use speech more. And if they were open to experiences, they would also use speech more. So here you can see our findings. In particular, we found that there was a significant relationship between how agreeable a person was and how many speech commands they used. So if a person, let's say, was inclined to cooperate more, they were less likely to use speech commands, probably because they were concerned about disturbing the other person while talking. And in this study, we, for example, logged the interactions of the participants. We also tracked their 3D position in the space in front of the wall. And one reason we did this is because we were interested in finding out if a speech interaction would actually be helpful to interact from a distance on the wall. Usually in front of wall displays, people tend to walk away from the display in order to get an overview. So we wanted to find out if speech was helpful in this sense. And so as you can see here, let's say not surprisingly, touch gestures were performed around 0.5 meter away from the screen. Of course, it's clear that people needed to stand close to the screen in order to use touch. And for the case of speech, we noticed that on average, people use speech commands where they were standing around 1.5 meters away from the screen, which suggests that they certainly use it successfully to interact from a distance. As you may notice from the heat maps, speech commands were used much less than touch, also following the chart I presented before. But as I'm trying to show you here, it was used for a specific task from a distance. And so finally, what I would like to tell you at the end of this presentation is talk a bit about the design considerations that we drew based on the findings of our study. We drew 5 design considerations, but to just give you a short preview here, I will talk about 3 of them. So the first one is what I mentioned before. The speech interaction was used for global operations. So in general, if someone is planning to design a multimodal system, one possibility that we suggest is considering leveraging speech interaction for global operations. This means operations that affect the whole data set. Our findings were also confirming previous findings of using speech commands in an individual scenario. So apparently, this applies for both individual and collaborative work. Another design consideration that we present at the end of the study is that speech supported both closely and loosely coupled collaboration. So for those of you who may not be familiar with this terminology, when 2 people collaborate, you usually say that they're closely coupled it's a closely coupled collaboration when they're working very closely with each other and talking about, for example, what they're doing, focusing on the same task. In this case, as you see in the picture, working on the same document. And loosely coupled collaboration is, for example, when people say, okay, we want to find something out, and then the people divide this task into smaller pieces and they both walk away, but they're actually still working together. And so in both these scenarios, we notice that people use speech interaction in the same proportion. So half of the speech commands in the study in general were performed during loose collaboration and half during close collaboration. And finally, something we also found out is that speech interaction helped each participant to be aware of what their partner was doing. So after they had the chance to interact with the system, we, for example, asked them in a questionnaire how they felt about speech, whether they were concerned about bothering the other person or whether they felt that they were bothering the other person when they use speech. And although 8 of the 20 people had this concern, 14 in total of them, so many more people actually said that speech helped them to be aware of what their partner was doing. So in general, in the paper, we concluded that speech interaction was not a significant obstacle, but could certainly be helpful for group awareness. And so to learn more about the design considerations and all our findings, I would recommend you to please check out our paper. Both of the papers I presented today are open access, and they also have a corresponding OSF project with all the supplemental material. Thank you.
Thank you, Gabriela. Really nice work. Kind of a nice follow-up from your previous paper. I was actually intrigued by the identification of these personal characteristics you described, right? Like agreeableness, etc. So I'm wondering how you envision addressing these personalized interaction choices to better accommodate everybody's, varied traits and preferences in these collaborative systems in a way that is effective to support equity across all these participants when they're interacting in a visual analytics context.
Yeah, I think indeed the fact that personality had a relationship with the interaction choices suggests that, let's say, we cannot really come up with one interaction design concept and expect everyone to, let's say, make the most of it. It really depends on the person. Of course, we look only here at 3 traits, and only one of them was relevant in this particular aspect. But our work suggests, of course, it's worth looking into also different tasks and how they can relate. In this case, we found that it would be a good opportunity to, for example, support 2 or more modalities as our system, so that if someone is very much into speech, they can do this. If someone's very into touch, they can do it. However, this may not scale completely, as in, for example, this case, people didn't use touch so much, and there were only 2 people. But imagine you would have 3 people, and then let's say 2 are talking, and the other one is in the background. Like there, we would need to conduct, let's say, a different study to find out how the group dynamics may be influenced by these choices. However, yeah, I would think similar to the, for example, accessibility aspect. In the end, everything indicates that the better way to go is to try to support one task in different ways, and then let the people, let's say, make their own choices. But of course, there may be some trade-off on, for example, in the case of speech, how much is the other person bother more or less by the use. But at least in our study, everything indicated that this may not be such a significant obstacle.
Okay, well, thanks for that response. With that, this concludes the collaboration and communication session. I see a lot of really nice discussion on Discord, so I'd really encourage folks to take advantage of that and continue your conversations. But let's give a round of applause to all the 6 speakers at this session, and thank you very much, and hope you all enjoy this virtually, and hope to see most of you in person next year. So thank you very much. And special thanks to the student volunteers. I know that they're working really hard in the background to just make things go smoothly. So thank you, SVs, as well.